to introduce Dr. Khaled Emam, professor at the University of Ottawa, expert in health data privacy and synthetic data generation. His work has a major impact in balancing data utility and privacy. He has experience of working with large data sets such as CHEO Research Institute, uh, electronic health records, mm, and creating a data platform to create synthetic data based on electronic health records, as well as synthetic version of Ontario's COVID-19 case database showing the utility of synthetic data. He's also founder of Replica Analytics, a company focused on generating protected synthetic data. He'll be sharing his insight on the growing role of synthetic data in health and healthcare. Please join me in welcoming Dr. Khaled Elema. Dr. Elema?
Okay, great. Thank you. And thank you everyone for joining us today. What I will do over the next 45 minutes or so, just give you a broad overview of synthetic data and its applications, how it was used, what kind of problems it can solve. The presentation is based largely on our work, but I've included references, and when you go through the references, you'll get a broader picture of the work of others in this space and their contributions as well. But I'll focus on the results from our work because I understand them the best. So let me start off by just describing what synthetic data is. The basic idea behind the type of synthetic data that I will talk about is that you start off with a source data set of some sort. This can be electronic health record, it can be a clinical trial data set, it can be a registry. And then you fit a machine learning model. So this is step one. Fit a machine learning model to learn the patterns in this source data. There are many different types of machine learning models that have been used for this purpose. And then once you've trained the model, you can use it to generate new data. And this new data is synthetic data. So the synthetic data is generated from the model. And because the synthetic data is generated from the model, in theory, there is no one-to-one mapping between the synthetic data here and the source data here. And therefore, that gives synthetic data its privacy preserving characteristics. And on the right-hand side, you can see an example of a synthetic data set. So the synthetic data can look very real. They'll have the same variable names, same format, and the same univariate and or similar univariate and multivariate distributions as the source data. So that's the basic idea. And some of the models here can be trained from scratch using the source data, or you can use pre-trained models, foundational models, or even large language models to continue train them or fine tune them on the source data. So that enables you to create these models or these types of generative models on small source data, because you're essentially using pre-trained models, which allows you to work with small data sets. And the basic structure of these types of synthetic data generation models or generative models is kind of two general architectures. One is, which is, the first one is shown here. You ingest a real data set, you train a generator, and then the generator creates synthetic data, and then you have an evaluator, and the evaluator would essentially compare the synthetic data to the real data and compute two metrics. The first metric is utility, and the second metric is privacy. And then based on the results of these metrics, you have essentially a score, which is then fed back here to continue training and fine-tuning the hyperparameters of the generator. And you keep iterating until you have a synthetic data set that balances utility and privacy. And I'll talk about both of those things, utility and privacy, later on. And the other architecture has the same idea, except that instead of giving the generator the real data, you give the generator some random input. and then the generator converts the random input into synthetic data. And then again, it's evaluated in the same way uh, until you're able to take random input and convert it to a synthetic data that has good utility and privacy characteristics. So at a very high level, these are the two general architectures that are used for uh, training a generative model from scratch on synthetic data. As I mentioned, you can also use pre-trained models, but I'm not describing those as they have a completely different approach. So in terms of privacy metrics, when you're able to generate synthetic data, um, the idea is that they are privacy preserving, and there are two ways to measure the privacy of synthetic data: membership disclosure and attribute disclosure. These are the two main types of metrics or types of disclosure that are relevant for synthetic data. We just did a consensus report recently here, which is available now in archive, which describes the body of work on evaluating the privacy risks in synthetic data. And where we landed in that consensus framework is membership and attribute disclosure are the two main types of inferential risks that are relevant for synthetic data. And when you're able to create privacy preserving synthetic data, then this slide shows you all the different use cases that you can apply with this data, from internal reuse to external data sharing. So for attribute risk, I mean, one metric we developed earlier on called attribution disclosure. But just at a very high level with attribution disclosure, so let's say this person is Sally, and on the right hand side is a synthetic data set. This record highlighted in yellow, Sally was born in 1989, is not Sally's record, because this record was generated from a model, but it matches Sally's characteristics because Sally is also female, born in 1989. So the basic idea then is, if we find a matching record, is that new information that we learn about Sally, which is this, it's NDC code, which is the drug code, prescription code for Sally. The question is, if we find a record that has the similar characteristics, a synthetic record with similar characteristics, do we learn correct information about Sally? And in this definition of attribution disclosure, we define a metric, and we can use that to evaluate whether we can draw inferences, correct inferences about Sally from the synthetic data. And then membership disclosure is the other type of metric. And the basic idea here is we have a real data set right here. So we start with a real data set. We synthesize this real data set and create a synthetic data set, so it's fine. And then an attacker would create an attack data set from the same population. And the question is the attacker able to determine? So this is Sally here, right? The attacker wants to determine whether Sally is in the real data set. The attacker is not able to determine which record belongs to Sally, but they only want to answer the question, is Sally in the real data set? If the real data set consists of, for example, patients who have HIV, and if the attacker determines that Sally is in the real data set, then the attacker would learn something about Sally, even though the attacker is not determining which record belongs to Sally. So it's an inferential process. So the way the attacker would do that is to match records from the attack data set, which includes information about Sally, with the synthetic data, and by using the synthetic data, make a guess of whether Sally is in the real data set or not. And there are different techniques for conducting these membership disclosure attacks, but essentially the main idea is to use the synthetic data to make a guess or make a prediction on whether Sally is in the real data set or not. And it's essentially, a classification problem, yay or nay, correct or incorrect classification, and then you can evaluate the risk of membership disclosure in synthetic data. So we've done a number of studies on this, on evaluating membership and attribute disclosure in synthetic data, but I'll just summarize one of the studies because I think it basically captures what we have learned so far. So this is a study we did on 8 different breast cancer clinical trials. So these are different clinical trials um, that were done over time. Some of them are single site studies, some of them are multi-site international studies, so kind of a cross section of um, of types of clinical trials. And we use 3 different types of generative models, so 3 different ways to generate synthetic data. The first one is sequential synthesis, which is essentially a statistical machine learning technique using decision trees. The second one is a GAN, generative adversarial network, which is a type of artificial neural network, and then a variational autoencoder, which is another type of artificial neural network architecture. And we evaluated the attribute disclosure. So we created synthetic data set for these clinical trials, and we evaluated the attribute disclosure for these different data sets. And a commonly used threshold for this type of attribute disclosure metric is 0.09. So as you can see here, that for all of the clinical trials, for all of the models, basically the risks are lower than our threshold. Um, so from an attribute disclosure, attribution disclosure perspective, this is the attribution disclosure metric I mentioned earlier on. The privacy risks are very small on these synthetic clinical trial data sets. And then from a membership disclosure perspective, again, the same 8 clinical trials. Again, the same 3 generative models here. Um, and the threshold that we typically use for this type of membership disclosure metric, the description of the metric is in the paper, but it essentially gives you an F1 score characterizing how accurate the adversary's prediction that a particular individual is in the real data set or training data set, how accurate that prediction is. And it's a relative metric. And as you can see, uh, almost all of the trials are have a low membership disclosure except this one. Um, but in this trial, the sampling fraction was very high. What that means is for that period of time, for this type of clinical trial, about 50% of the studies that were being conducted uh, 50% of the patients that were being enrolled in trials of this type at that point in time were in this particular trial. It was a large trial. So the chances of being in the training data set was already 50%. So um, the sampling fraction was already quite high, which makes it very difficult to uh, for individuals, it makes the membership disclosure high by default. So in this case, the membership disclosure was high, but for all the other ones, it was quite low. So what this has, and this is just some um, example of an evaluation. We have done a few more studies and with observational data, real world data, as well as other clinical trials, and the results have been generally quite consistent in that the attribute and membership disclosure metrics have been below the thresholds that we have used. So the main conclusion from a privacy perspective is that generative models cannot, unless they're trained and as I showed you in the earlier diagram, if privacy is embedded within the training of the model, then you can ensure that privacy is low when the um, model is trained. But in most cases, privacy is not included as part of the training, it's calculated afterwards. So in those cases, um, you can evaluate or measure the privacy risks after the fact when the data is generated, and we have good metrics now and good consensus frameworks and benchmarks to determine whether these privacy risks are small enough or not. And based on the evidence so far, the privacy risks have tended to be quite small based on the 2 metrics that are important for synthetic data, which is attribute and membership disclosure. Okay, so now let me move to utility, and I'll spend a bit of time on the utility of synthetic data. So utility is essentially how useful is the synthetic data. I mean, it's great that it preserves privacy, but so what? If the If the data is not useful, if it's not a good proxy for real data, then that's problematic. So you can also evaluate the utility of synthetic data in different ways. One way to evaluate the utility of synthetic data is to do expert discrimination, where you get experts, domain experts, which in this case would be clinicians, and give them, say, 50 records that are real and 50 records that are synthetic, and then see if they can tell the difference. And if they cannot tell the difference, then your synthetic data is good because experts cannot discriminate. But if they can tell the difference, then your synthetic data is not good. So that's one approach. The problem is, of course, it's very time consuming and you're limited in how often you can do this because you need to recruit experts and have them available to do this kind of manual process. So the two ways we're going to look at um, utility are really fidelity and replicability. And these are the most common ways because they can be automated. So fidelity looks at um, how similar the multivariate distribution of the synthetic data is to the real data. So it essentially determines um, how well the synthetic data is able to reproduce um, the distributions of the real data. It doesn't tell you whether the data is useful for anything. It just tells you how well it resembles and retains the patterns in the original data. And there are a number of different fidelity metrics that have been developed. Replicability is a different way of looking at utility, and it's considering whether you're able to replicate the results of analysis using synthetic data. So if you do an analysis with real data and analysis with synthetic data, are you able to get the same results? So we're going to focus mostly on replicability, at least in this presentation. There's a bunch of different fidelity metrics that have been developed, and so we're not going to talk about those today. We're going to focus on the replicability approach to evaluating the utility of synthetic data. These are not the only ways to evaluate the utility of synthetic data. You can look at other ways of evaluating utility. For example, you can look at fairness metrics. You can look at the degree of hallucination. So there are a number of things you can look at, but the main ones are those, fidelity and replicability. And today we're going to look at replicability. So from a replicability perspective, the basic idea, as I mentioned, you have the real data set, you perform some analysis, you create a synthetic data, and you repeat the same analysis on the synthetic data. So the analysis is exactly the same, but on different data sets. And then the question is, are the results the same? Are you able to replicate the results produced from the real data when you perform the analysis on the synthetic data? So I'll show you some examples here of some studies we've done over time to try to answer this question. So this example was the COVID-19 database from Ontario. Uh, and um, this was data that was collected until the end of November 2020, so the first few months of the pandemic. And we trained a gradient boosted decision tree to predict mortality. And we created a synthetic version of the data set, and then we had the real data. So you can see here the real and synthetic variants, and basically the x-axis is the number of days since the 1st of January 2020. And then the y-axis is the mean probability, predicted probability of death using this gradient boosted decision tree, which is a form of machine learning model. And as we can see, for quite a complex nonlinear pattern, the synthetic and real data were quite close to each other. And then, of course, you can see here kind of around the end of November, this is the second wave was starting to pick up again. But there's strong concordance between the real and synthetic data and prediction of mortality over time. And the second one was analysis on the same data was to look at age. So again, here we have the age groups. And on the y-axis, again, it's predicted mortality. And as you can see, there's strong concordance of between the real and synthetic data between the for the prediction of mortality. And of course, as we know, the probability of death was growing very rapidly for older individuals, at least during the first months of the pandemic. And the numbers up here are the confidence interval overlap. So this is the mean value and the confidence interval, and here we computed the confidence interval overlap from these predicted values. So again, very high confidence interval overlap between the real and synthetic data set. So this is an example of being able to replicate the results of analysis on a real data set when we are training machine learning models to capture quite complex and nonlinear relationships among the variables in the data set. When we're doing statistical analysis, however, when we're trying to train, regression models or survival models, we have to think about something else, and this is very important. So, because synthesis is stochastic, so every time you create a synthetic data set, you get a different data set because you're sampling from the model. Essentially, you're generating new data, and every new data set is different. So the right approach is you would generate 10 data sets from your model, and then you perform the analysis 10 times. So if you're training a regression model, you do the analysis 10 times. And then there's a series of combining rules that are used to combine the results of the 10 models. And then that is your analysis result, which is the combination of the model parameters from the 10 data sets and 10 analyses. This is quite similar to multiple imputation. So if you're familiar with multiple imputation, it's exactly the same idea. But the basic objective here is effectively to average out the stochasticity introduced by the synthesis. So that's how you would normally perform an analysis on synthetic data. So I'll go back here to our again, use my 8 clinical trial example. And as you can see here, the sample sizes vary from small to large. And we evaluate the performance of so here we replicated the published study. So we created a synthetic data set 10 times, and then we repeated the analysis 10 times and then combined the results. And then we looked at 3 criteria. The first one is estimate agreement. So it's the extent to which the estimate of the parameter on the synthetic data is within the 95% confidence interval of the real data. Decision agreement is whether the statistical significance and direction of the parameter in the synthetic data is the same as the real data, and then the confidence interval overlap for the 95% confidence interval for the synthetic and real data. And these are commonly used. So these 3 are commonly used criteria for evaluating replicability of studies. And here we did it for in most of these studies, it was the primary analysis that was published. So we essentially tried to replicate the published analysis for the 3 for the eight clinical trials using the 3 different models. And the main conclusion in this particular case is that sequential synthesis performed quite well, in that estimate agreement and decision agreement was true for all the studies. This particular study was a descriptive analysis, so there was no inferential analysis that was done. So decision agreement didn't make sense. But in all the cases where it made sense, estimate agreement and decision agreement were true, and then confidence intervals were high, and the results for GANs and variation autoencoders was kind of so-so, right? You had some cases where estimate or decision agreement were not high, and then the confidence interval overlap was not high. So the main conclusion from this is that you can let me just the main conclusion is some models are good, but not all models are good all the time. So generative models have to be chosen to reflect that are suitable for the particular data set that you're working with, because what we've noticed is some generative models work well in some data sets, but don't work well on other data sets. So in this case, we found that sequential synthesis worked quite well on these 8 clinical trials, where GANs and VAEs did not work well from the replicability perspective. We were trying to replicate the utility of replicate the analysis of the 8 clinical trials. So the reason why you have to do 10 data sets, generate 10 data sets when you're creating synthetic data, is basically as follows. I'll show you the simulation we did. So in general, when you have a population, you hypothetical population, you have some samples. So really, you have a sample from some population. You compute some sample statistics, and then you try to draw conclusions from your sample statistics, some effect size. But when you create synthetic data from the sample, yeah, then you also compute the same sample statistic, and then you estimate the effect size also based on your synthetic data, which is drawn from your sample. Um, so what we wanted to find out was, which is very very important, is to what extent is the synthetic estimate of the sample size a valid inference about the effect size in the population? Because that's really what we want to do when you're doing um, analysis. You want to draw population inferences. So we wanted to know how good are the population inferences that you draw with synthetic data. All the examples we looked at so far, in terms of replicability, we were comparing these two things. We were comparing the effect size from the real data sample to the effect size in the synthetic data sample. But now what we want to do is find out how good the synthetic sample inferences are relative to the population itself. So we did a number of simulations, and the typical ways you evaluate um, population inferences, you look at things like bias and power. So I'll just explain to you this what these graphs are showing. The x-axis here is the number of data sets we generated. So remember, I said we generated multiple data sets and then we use the combining rules to combine them. So for example, 10 here means that we generated 10 data sets and then we combine the results from the 10 data sets. And then the numbers up here is the amplification. So times one is we generated a data set of the same size as the original data set. Here, data set size is twice as big, 5 times as big, and 10 times as big as the original data set. And the straight line as the real data. The dashed line is the analysis without combining data sets, and then the kind of dashed dotted line is the results when we apply the combining rules. So with respect to bias, we want the bias to be equal to 0. So we approach 0. We're quite close to 0 at around 10, combining 10 data sets. And we were not when we're not using the combining rules, you can see here that the bias can be high. But the interesting thing is that when we amplify, so we think that by amplifying the data set, we have more observations, etc. But the combining rules actually reduce the impact of amplification. And we can see that the bias remains more or less close to 0 all the way through, even after amplification. If we look at power, we want power to be around 80%. So, for the real data, we designed it, we designed the experiment so that the power is around 80% for the real data. And again, we can see that the combining rules achieve almost 80% at 10 observations, and that remains more or less correct even with amplification. This is for one of the data sets. We repeated this on multiple data sets. And then the other thing, you look at coverage. So you want your coverage to be 95%, coverage of your confidence interval. And again, the same thing around 10 data sets, you get more or less, 95% coverage. And it's consistent even with amplification. And then empirical standard error, you want it to be as close to 0, and you kind of start to plateau at around 10, even with amplification. So the main point of all this is to say, if you want to draw valid inferences with low bias, proper coverage, adequate power, or correct power, then you need to generate 10 synthetic data sets, perform the analysis 10 times, and then use the combining rules in order to draw valid inferences from your synthetic data. Otherwise, as you can see here, the dashed line, in all of these cases, the dashed line here, for example, for your coverage, um, um, if you don't apply combining rules when you're performing a statistical analysis on synthetic data, your coverage can be wrong. And as you can see here, your power can be wrong, and completely inflated as you amplify, if you try to amplify. And then your standard errors, empirical standard errors, are not approaching 0 here when you're using single data sets. So all that to say is, if you're trying to draw population inferences from synthetic data using only a single data set and training or fitting models, with just that can be misleading, and therefore you need to generate 10 synthetic data sets, use the combining rules to determine your parameter estimates and your standard errors to get valid inferences from your data. And in general, generate 10 data sets and average if you're doing a prediction model, average the AUC or the accuracy of the model across 10 data sets to get a more reliable estimate of the model accuracy using your synthetic data. And we observed that works quite well. Like as a general rule, generate 10 synthetic data sets. So now we can generate replicable results. So if you do that, then synthetic data sets can be a very good proxy for real data, uh, but you have to be thoughtful about the choice of generative model because not all generative models are created equal, and some of them work better for certain data sets. Um, so that's kind of the main conclusion from the studies that we have done so far. Okay, so we've talked about privacy and utility. Let's talk about a few other things. Um, One of the questions that came up over time was, can we do federated analysis using synthetic data? So the whole idea is that can we combine synthetic data sets or real data sets, pool them as a way of data sharing across jurisdictions, and then get valid analyses. And so there was a real scenario here where the objective was to pull data from McGill and University of Vienna. Um, and the objective was to build a model, train a model to predict or capture cardiovascular health. So we used the StatScan CCHS data sets, and then the Austrian data was the ATHIS data set, which is another survey done in Austria. And both data sets were harmonized. So, but we wanted to pool them, and we couldn't share the data, right? We couldn't share the Canadian data, and the Austrians wouldn't share their Austrian data. So we said, okay, well, let's see if we can come up with models to evaluate or to share data across jurisdictions. So we did two things. First of all, we created a federated learning platform. So we used the Data Shield software, which is an open source tool that allows you to do distributed computation without sharing any raw data, and it's used good for fitting regression models. So we implemented two nodes, one node in Montreal and one node in Vienna to do this federated analysis. And Data Shield doesn't distort your data, so that gives us the ground truth. And then we took the Canadian data, we synthesized it, we did a privacy assessment, validated that the attribute and membership disclosure risks were very small. And then we sent the synthetic data to the Viennese team, who then pooled the Austrian data with the Canadian data. And then we built a regression analysis model with the pool data. And then the federated analysis also gave us results, and we compared both of them. So again, we looked at the Canhart score, which is a standardized measure of cardiovascular health, and we fitted, and it's just a simple, in this case, least square regression model. And this is one of the models we fitted, which was the main effects model. The main conclusion is the model results are very similar to each other between the federated analysis and the pooled analysis using partially synthetic data. So that's the Canadian data is synthetic and the Austrian data is real, and they were pooled. So the model parameters, the estimates, the confidence intervals were very similar between the two. And so in fact, that the synthetic data can be used to share data across jurisdictions, and you get more or less the same results. The main difference between those two approaches is that it took us a year and a half to set up the federated analysis system and a couple of weeks to do the synthetic data analysis. And the reason it took a couple of weeks is we went back and forth to adjust the models here and there while we're doing the analysis. So actually, synthetic data analysis happened very quickly, like I said, a matter of a couple of weeks, with iterations versus a year and a half to set up a federated analysis platform. So the main conclusion from this was that it's plausible to use synthetic data as a way to share and pool data sets across jurisdictions and still get the same results. In this case, we generate 10 synthetic data sets and use the combining rules, etc., for this analysis for the synthetic data analysis. Okay. The other scenario that we encounter very often is small data sets. So, roughly for clinical prediction models, the number of observations that are used are between 250, 300, and 550. Kind of that's the common range. So most data sets are quite small. But if you want to train machine learning models, there's a lot of additional power and advantage to training machine learning models when you want to do prediction, because some of these models can be quite powerful, but they require a lot of data. So what we wanted to ask is, can we use generative models to augment small data sets? So we did a study, and again, we looked at this are all observational data sets. So we have 7 data sets here, and we developed a methodology to augment small data. So this is the amount of augmentation. So whatever these so hot flashes was, that data set was around 300 observations, and then we added 720 observations to it, augmented using, these are different types of generative models. Again, a VAE, this is a Bayesian network. And then we evaluated the AUC, which is the area under the receiver operating characteristic curve, which is a common measure of prediction model performance. So we said, look, we have our world is small data. We are based at a children's hospital. A lot of our data sets are small. If you're working with rare diseases, your data sets are going to be small. But even then, in general, even for adult data, the data sets are typically in 350, 400 range. That's kind of a normal range for clinical prediction models. So we looked at the AUC results. So you have the baseline result for the models, the augmentation, um, and so how much the model performance improved after augmentation was done, and then the relative improvement in the AUC. And then we just compared it to resampling. Said, well, look, why don't we just resample with replacement from the real data to augment it and just use that as a baseline. So the main conclusion is that the average improvement in AUC through augmentation is 15.5%, which is actually quite significant. Even half of that would be quite significant. It's a very big improvement in model performance just from augmentation. Um, so that's another use case for synthetic data models or generative models, is that you can use them to augment small data sets. It doesn't work all the time. So as part of this work, we evaluated under which conditions does augmentation actually help. And so if your data set is very large, then augmentation doesn't help. If your data set is very small, it probably wouldn't help. So there's a sweet spot for augmentation being valuable, but it turns out to be the same sweet spot that we typically encounter in clinical when training clinical prediction models. So synthetic data generation can be used for augmentation, in this case, to improve machine learning prediction. And in all of these studies, we used light GBM, gradient boosted decision tree model, to do these prediction. And these were all binary prediction problems, or binary classification problems. And the details are in this preprint, which is shown at the bottom. Okay, the other type of augmentation that we looked at was insufficient accrual in clinical trials. So one of the big problems we see often is clinical trials, especially academic clinical trials, um, is that they don't reach target recruitment. So you want to recruit 800 patients and you end up recruiting only 600, and you run out of money and run out of time. And there are many reasons for this. And the problem with insufficient accrual is either the trial is abandoned, so you put all these patients through the treatment or the control or the process of participating in the trial, and then nothing is learned, or very little is learned from the study because we're not able to reach target recruitment. Or the investigators try to draw conclusions from the data that's collected, which basically means you're trying to draw conclusions from underpowered studies, which is not ideal. So the question we wanted to answer is, well, look, can we use the data that's already collected? So this data, so let's say you conduct a study, and then at this point in time, you run out of money or time or resources, and you can't continue the trial. The trial has been stopped for whatever reason. So the question was, can we train a generative model on this data and simulate the rest of the study, right? Um, and then if we simulate the rest of the study, will we draw the same conclusions as the original trial? So again, we looked at breast cancer, and we obtained data from 9 breast cancer clinical trials, and we simulated accrual problems, and we evaluated different types of generative models to um, simulate the remainder of the study. So let me walk you. These are kind of the main results, but I'll just walk you through these graphs. So the missing ratio is basically what proportion of the last recruited patients was removed. So 0.1 means we took the completed study, clinical trial, and removed the last 10% of the patients. Doesn't matter whether the treatment arm or control arm, we just remove the last 10%. And then we use the generative model to simulate those 10% patients, and then generated 10 data sets, use the combining rules, did the analysis the same as the published study, and we see if we can replicate the published study. for the 10, sorry, it was 9 clinical trials, 10 analyses, because one of the trials had two endpoints. And then 0.2 is remove the last 20% and so on. And 0.5, remove the last 50%. And so the best two methods turned out to be bootstrap and sequential synthesis. Sequential synthesis was, in general, a little bit better. I'll show you why. And we looked at the same criteria, estimate agreement, decision agreement, and so on, as our previously explained metrics for evaluating replicability. And as you can see, up to around 40% um, removal, the results on sequential synthesis are pretty good in that across all 9 trials or 10 analyses that were done, we're able to achieve 100% estimate agreement, 100% decision agreement, um, and for confidence interval overlap, it was above 0.8. That's just above 0.8, up to 40% removal. And then the standardized difference, we're essentially looking at how different the parameter estimate is between the real and synthetic, as the simulated data or the augmented data. And in all cases, there's no difference. So these results are very encouraging. We did some additional analysis to find out why this is happening, and we found that we think one of the reasons is that patients recruited early in the study are similar on the effect size to patients recruited later in the study. So, and that makes sense because then patients in the early part of the clinical trial tend to have the same effect size to later patients, so you can use the earlier patients to train a generative model and then simulate the rest of the study. Up to 40% accrual deficiency, which is quite remarkable. We don't know if these results will be replicated in other contexts and so on. This is exactly what we're trying to do, but the results are very encouraging in that as a reliable method to simulate additional patients, you can use sequential synthesis to continue the simulation and drawing conclusions from your clinical trial. Okay. The other thing you can do, again, related to augmentation with synthetic data, is mitigation of bias. So here we have, and this is the last example I will show, and then we can take questions. So here we have a biased data set. We have, two groups, and the green group is missing people. So there should be more greens in the data so that the data set is representative of the population. But the actual data set here, it only has these number of green people or green groups, but in fact that's underrepresenting green groups, which is in this case looks like females. Females are underrepresented in this data set compared to the population. So then the question is, well, can we use the data set that was already collected to simulate more females, and would that be valid? Can we get the same results? And this is for observational data now. It's not clinical trials. So again, we did a study to evaluate this and to what extent can generative models be used to compensate. And this is essentially the workflow for the study. The only thing I will emphasize is we define the ground truth consistently, and we compared different approaches. So undersampling, oversampling, SMOTE, probability score matching, machine learning methods, and then SMAs, essentially generative models. And then we compared on the debiased data set using all these methods on the same test set. So we had the ground truth consistent and here the same test sets to compare against. We compared against the prediction accuracy. Brier score is a measure of calibration, odds ratio, because these are all logistic regression models, confidence interval overlap, and we calculated fairness as well. So just to give you a quick answer, I'll just explain what these charts show. So for every, we had multiple data sets, and for every data set, we removed a certain proportion of a particular group. The particular group can be females, can be folks with a particular disease or low socioeconomic status. Depending on the data set, we biased the data set. And essentially, the x-axis here is the extent of bias. Okay, so the more x means more bias is induced in the data set. And then we simulated patients to compensate for the bias and then compared the analysis of the debiased data set to the original analysis without bias in the data set. And so this result just shows the impact of bias without any debiasing. And as you can see that as you bias data sets more, like once you reach like around 50% of bias, the impacts on the odds ratio here, starts to become very large. The AUC seems to be more robust, but still it tends to deteriorate after it's kind of good after 50%, but then deteriorate after 50%. And this is the AUC, which is the prediction accuracy for the minority class. And here we simulated different kinds of bias. So, marginal bias is just simply removing patients in the bias group, and then CB1 and CB2 are just different types of more complicated bias where the bias depends on some other factors. And here are the metrics. So as expected, as you introduce more bias, your fairness metrics tend to deteriorate quite rapidly. In general, you want these to be um, close to the ground truth, to the starting point. So you don't want uh, well, of course, the biasing will impact fairness. So SPD, EOD, and AOD are three different bias metrics. And as you can see, as you bias, your fairness deteriorates, which is expected. Now, here's the result of the debiasing. So two methods were the best. Random oversampling, essentially bootstrap again. Like random oversampling seems to be a recurring theme here. That's actually quite an effective method, but generative models tend to work better. Um, the main conclusion is, we looked at odds ratios, and the SMA, which is a green line, tends to perform pretty good compared to other methods for the odds ratios for the different. It's the best method for the three different types of bias. For model accuracy, it's also the best method for the three different kinds of bias. And then for minority AUC, it's the best method for different types of bias. And the same thing for fairness metrics. It also performs well on fairness compared to other methods. So all that to say is we can, if the bias is small to moderate, we can use generative models to debias data sets by simulating addition individuals from the minority group. And this will make some good adjustments to the odds ratios and ensure that the AUC is better. It maintains the AUC, and for the full data set and the minority AUC, and improves your fairness metrics, of course. So it's another application of generative models. But if your bias is very high, high or extreme bias, then it doesn't work. The impact is, as you can see here, that in general, when bias is high, the odds ratios, even for marginal bias, which is a very simple type of bias, doesn't really help very much. And then here, you can see that for AUC, that when bias is high, the adjustments don't really work that well, which is not very surprising. So for small to medium bias, we can generally adjust for it in a reasonable way, but for extreme bias, for observational data, we can't really adjust for it as well. So the main conclusion is, beyond data sharing, uh, synthetic data can be an alternative to federated analysis, in the sense that you can create synthetic data sets and verify their privacy, and then share them, and then pool the data sets, and then perform the analysis on the pooled data sets, and you'll get more or less the same answers as you would had you set up a federated analysis system, and then the time to results can be much faster. But also there are a number of augmentation scenarios. We can augment small data sets to deal with kind of the machine learning training problem. We can improve the performance of machine learning models through augmentation. We can help with the insufficient accrual problem in clinical trials by simulating additional patients for trials that are not accruing enough patients. And we can use augmentation also to deal with bias problems. So augmentation using synthetic data can solve a number of different problems. So that's the summary of synthetic data, what we've learned so far. So we know how to measure privacy. We have consensus on privacy metrics. We have a framework for evaluating replicability, which is probably the more important way of evaluating the utility of synthetic data. Not the only way, but an important one. Probably one of the more important ones is replicability. Is to what extent can synthetic data be a proxy? And we have evidence from machine learning studies and statistical analyses that it can be a good proxy, but you have to use the 10 data set and combining rules to get more reliable results, and then augmentation scenarios that I mentioned. I'll stop there and see if there are any questions.
Thank you so much, Dr. Emam, for this very enlightening presentation. There are some questions in the chat. I could read them to you if you'd like.
Sure, that'll be fantastic.
Okay. First question is from Bhavya Patwa regarding replicability of metrics, utility of synthetic dataset. Let's say for machine learning task, would the utility of synthetic data be limited by that prediction task, or is there research that shows it can extend to some other prediction task?
Well, I mean, what we know is that the you have different metrics for evaluating prediction performance, prediction accuracy, and if you average those across multiple data sets, then you get more reliable results. So it's not limited to a single metric. It can be applied to multiple prediction performance metrics, but general recommendation is average them across multiple data sets. And also for the prediction itself. I mean, if you are making a prediction from a synthetic data set, uh, you will get more reliable results if you train 10 models, make 10 predictions, and average the predictions across the 10 data sets.
Yeah, that makes sense. Like in a way that if you want to make a study about, let's say, it's about the utility of like groups of synthetic data, but let's say if you want to like share, let's say, share synthetic data with some people who want to like use it for a certain task, that they want to work on, then would that be, you know what I'm saying?
Well, share 10 data sets. I mean, that's our recommendation. So they can do the task 10 times and then combine the results from that. It's more reliable because what we've observed is the stochasticity can be quite high. So you want to average across that.
Yes, but like generally, let's say if you're working under like a research center or something like let's say we are limited to one data set, right? Like we don't have access to 10 data sets. Like let's say we have access to one, and we want to like if you want to like share a synthetic data set of from that one real data set,
Yeah, but
and
you start with one real data set. You always start with one real data set, and then you train one generative model, and then you generate 10 synthetic data sets from the generative model. So you're not starting with 10 real data sets, you're working with 10 synthetic data sets that are trained on a single real data set, right? So
yes, yes,
I'm not saying you need 10 original data. You need one real data set as you normally would.
I see.
Train one generative model or your favorite generative model, and then generate 10 synthetic data sets from your generative model.
I see, I see.
Yeah.
So let's say if a research group would want to like let's say a research group within a center wants to like use let's say you said like 10 synthetic data set, but they don't know what kind of prediction task they're gonna work on. Like if let's say that's unknown, then uh, you know like for example out of distribution prediction task, let's say something like not out of it like the predictions task that is like not that a synthetic data is not evaluated upon. Like do you think that would be useful?
Yeah, I mean the generation the training of the generative model doesn't would normally not take into account the tasks. And if it's a good generative model, then that's okay in the sense that you should be able to uh, train multiple types of models for different types of tasks using the synthetic data, the same synthetic data, because it should be retaining the patterns in the original data. That's the idea, is that you don't need to know the eventual tasks. The studies on replication I was showing you just to make the point that synthetic data is a good proxy for real data. So if you generate synthetic data um, and you do all the things that are presented, then we have evidence that your results on the synthetic data are replications of the results you get from the real data. Um, but we did not train generative models for that specific task. Generative models were trained generically without taking into account the task.
Got it. Thank you.
Okay, you're welcome.
Thanks. Then I have two questions in one. That would be from Yasin and Cameron, who were asking, do you have any tools or library for evaluation of privacy and utility developed by your team that you recommend? And Cameron is asking also that, is there any tool or library to implement different models to generate synthetic data?
We have a package called PySDG that is available on, we can access it through OSF. So you go to OSF and search for PySDG. So that's the Python library that we use for our research. That it embodies everything we have. So I think right now it includes 8 different generative models. And let me see if I can put the link in the and then a number of metrics that we're continuously adding and improving. So that's the one we're using. That's essentially our research tool. So we're definitely investing in keeping it updated.
Amazing, thanks. Oh, cool. Two people have been sharing it. And last question was from Cameron, who was asking, could you please discuss synthetic data generation with other data types, such as imaging or time series, for example?
So I don't know much about imaging. I know there's a large body of work. So imaging, I'm not going to opine or comment on that. All I'll say is that for images, there's a large body of work as well. And the criteria they use for evaluation are different. For time series, there's also a large body of work for time series and for longitudinal data. So not just time series, but longitudinal health data, which is a lot more complicated than time series because you have multiple events per patient, and different patients will have a different number of events, and events can be of different types. So you can have, half a dozen or a dozen different types of events, drugs, lab tests, admissions, discharges, etc. Different types of events that pertain to individuals along a series. So longitudinal data is more complex than time series, and there is a body of work as well on different types of generative models for um, uh, capturing these types of longitudinal patterns and learning them, and then be able to simulate patients accurately um, um, based on the patterns that have been learned. So this is an ongoing active area of research, but I would say there's some pretty good models. We've done some work. I didn't show you the results from that here. We did a study with Alberta looking at opioid use, and the results were pretty good. There, in that case, we trained an LSTM, but that was a few years ago, and there are even more advanced models now that have been published by others for longitudinal data, which is, I mean, a more complex version of just time series data.
And there's one last question, which is there any plans to properly release fair source code for PySDG?
Eventually we'll release the source code for PySTG. Right now, we're just releasing the wheel files so that they can be used. But eventually, we'll make the GitHub repository. Actually, the GitHub repository only has the wheel files. It doesn't have the source code. That's correct. We're eventually going to make it available. It's just we're continuing to do some testing and so on. It's because it's in active development right now. And but yes, the plan is to do that eventually. I just can't tell you when because when it reaches a stable point, I guess we'll do that. But we're sharing the wheel file anyway, so others can still use the same tools that we're using, replicate the studies, um, and use the same types of generative models and the metrics as well. We're adding all those metrics that I mentioned. They're being incrementally added to the package.
Amazing, thanks. I think we're on time. Please join me to thank Dr. Emam for his presentation today. And for the recording, you will find it on the Mattermost forum that I shared upper in the chat. I will share it again. You just have to join this forum, and then we'll share it in one of the general thread. Thank you so much for your time, and all of you have a good lunch.
Thank you. Bye.
Bye.
Thank you.